Good. All righty. So my presentation today is on astrophysics and stuff. Actually, it's just astrophysics. There's no stuff. Sorry to disappoint you all. All right. So let's get started. Oh yes, I think so. I personally feel very bad about what they did to Pluto, and I don't agree with it. And I've made my stance very clear on that. All right. So a couple notes before we start. I do encourage questions. You can feel free to ask questions during the presentation. We're going to talk about special relativity, we're going to talk about general relativity, and then we're going to talk about black holes. Some of this stuff is counterintuitive. If you have no exposure to this or little exposure to it, it might seem kind of weird. So don't worry about asking questions. If you think something's odd, probably everyone else does too. So feel free to raise your hand. We will do kind of a general Q&A at the end. So if you want to ask random questions about the Big Bang or dark energy or whatever you want, assuming we have time, we'll do that. That's not a stump the physicist section. So if you want to just ask complicated questions to find something I can't answer, Victoria, please don't do that. Spoiler alert, there's plenty of things I can't answer, so we don't need to waste everyone's time finding that out. So without further ado, all right. In 1905, a complete unknown by the name of Albert Einstein had 4 scientific papers published, which was remarkable for a couple reasons. So for one, if you weren't a prominent scientist or associated to a prominent scientist, at this time it was pretty difficult to have any papers published. But more importantly, these papers answered some questions that had been vexing the scientific community for a number of years. So one of the papers explained the physics of Brownian motion, one of the papers explained the photoelectric effect, and then the last 2 papers, which we're about to talk about, covered special relativity and the mass energy equivalence. Special relativity dealt with an issue that had been bothering people for some time. If you measured the speed of light under certain circumstances, you got bizarre results. This was a known thing. Einstein was determined to figure out the significance of this. So his theory of special relativity contains 2 main postulates. One, all laws of physics are the same for all uniformly moving frames of reference. We'll explain what that means, but when I say uniformly moving frames of reference, I mean not accelerating. That's the important thing you need to remember. And also sometimes I may just say inertial frames of reference, it means the same thing. The second postulate is that the speed of light is constant for all frames of reference. Now when you combine these 2 things, Einstein came up with a really interesting conclusion. He reasoned that all motion is relative. There's no such thing as absolute motion. Your motion is relative to the objects around you, and that is the only way to define it. And that the frame of reference you use to measure this motion is completely arbitrary. It doesn't matter. And so we'll talk about exactly what that means. Let's start with a little example. In terms of relative motion, here on Earth, we all have a pretty constant frame of reference. We're all on the same planet. So generally we agree about most things. If I'm standing here and I walk to the other side of the room, we'll all agree that I was the one moving, not the room. But you could make the argument that I was stationary and the entire room, including all of you, moved past me in that direction. Now, that probably sounds really stupid. Look, Topper, we saw your legs moving. We know you were the one walking. But keep in mind, Einstein was talking specifically about non-accelerating frames of reference. So imagine that instead of walking to the other side of the room, I just sort of glide over there. I don't feel friction with the floor. I don't feel air resistance. There's no forces acting on me. It would feel, for all the world, that I was perfectly stationary and the entire room moved past me that way. What Einstein said is that that is accurate. My interpretation of that event would be correct, and it would be just as valid as anyone else's interpretation of that event. So consider you're a spaceship, or you're in a spaceship hanging in space. You have no objects around you to determine relative motion. If you see a spaceship come towards you and then go past you, you would probably reason that you sat there still the entire time and you saw a spaceship move past you. But if you're an observer on the other spaceship, You would say, well, no, I was still the entire time, and you moved past me in the opposite direction. The point Einstein was making is that both of you are correct. Both frames of reference are equally valid. So, keeping with this relative motion theme, let's consider I'm standing here, and I throw a ball at 10 meters per second to the other side of the room. You'd measure the speed, I'd measure the speed, we'd all agree it went 10 meters per second. But now, let's consider I am driving through this room on a vehicle of some sort for some bizarre reason, and the vehicle's going 10 meters per second, and then I throw the ball at the same speed. From my perspective, the ball goes forward at 10 meters per second. But you are all stationary with respect to my vehicle. So you would see the ball going forward at 20 meters per second, the speed of the vehicle plus the speed of the ball. Light behaves differently under these circumstances. If I were to shine a beam of light forward, we'd all see it go forward at 300,000 kilometers a second. We'd all agree on that. Now I'm on my vehicle. I shine a beam of light forward. I measure 300,000 kilometers per second. You guys measure it. You would measure the exact same thing, not 300,000 plus my 10 meters per second. We would measure the exact same speed for the speed of light, even though I'm moving and you're not. So the only thing that we can agree on in our frames of reference is the speed of light. Now here on Earth, this isn't really a thing you ever notice, because 300,000 kilometers per second plus 10 meters per second is not a noticeable difference. But let's imagine we were traveling at a significant speed. You would still see the same speed of light as I whizzed by you. So in order to keep time, we're going to build a time clock. So imagine you've got two mirrors, and you shine a beam of light between them. And as the light bounces up and down, we use those ticks to keep time. What did I just do? Or somebody left. All right, so I'm on my spaceship. Now I'm flying through the room at half the speed of light. And I've got my time clock in front of me, and I see the light beam going up and down, perpendicular to the ground, just straight up and down. But as I go past you, you all see the beam moving at an angle. Now, we measure the same speed for the light beam. So what does that mean? Well, you can calculate the difference we measure in our time. And actually, it's high school level math. So I'm going this way. The light beam's going this way. You see it going this way. So velocity, distance over time. So distance equals time times velocity. So you saw me go at speed v, and we'll call your time t. This is the distance that the light traveled in my time, which we'll call t naught. And this is the distance the light traveled in your time. So, I don't remember what to do with right triangles, right? Pythagorean theorem. And then it's simple algebra. If you solve this for t, you get this guy, the equation for time dilation. The time that you measure will be greater than the time that I measure. And the faster I'm going, the more significant the difference between the two times. So if I'm flying through here at a relativistic speed, I would appear to you to be moving in slow motion. Now, to me, while I'm on the spaceship, everything seems normal. I'm moving at a normal speed, nothing seems out of the ordinary, and there's nothing that I can do to tell me that someone else is viewing me and I look like I'm moving in slow motion. But what if I look over at you? Now imagine, as I fly by, you guys have the time clock. I see the exact same thing that you saw before with the light moving at an angle. So if I were to measure your time, I would think you were moving in slow motion. I would get a greater time than you would measure as I passed. So both of us experience the same thing with respect to each other. Now, again, there's no test that you can do to let you know that you look like you're moving slowly compared to someone else. Same thing with me. I have no way of knowing that I look odd with respect to you guys. So when we take these measurements, Einstein reason, our measurements are completely valid. Your measurements are, my measurements are, even though they completely disagree, both of us are right. The only thing we agree on is the speed of light. Now, to get an interesting example of what the significance of this is, consider what's known as the twin paradox. So you have twins that are on Earth, and one of them decides to go off on a high-speed joyride for some reason in a rocket ship. So as he leaves, he's traveling at a high speed, and the twin on Earth sees him and sees him slow down. Now, the traveling twin looks back at his brother on Earth, and he sees the guy on Earth moving in slow motion. So what happens when the twin comes back? Well, we can calculate it. So if the traveling twin moves at half the speed of light for 1 year of his time, 1.15 years will have passed for the twin on Earth. If he goes at 87% the speed of light for a year of his time, 2 years will have passed on Earth. If he goes at 99.5% the speed of light, 10 years will have passed for the twin on Earth. But keep in mind, he's seeing the twin on Earth move in slow motion. So what happens when he gets back? Who's the older one? Does anybody know? One on Earth is older. Why? All right. So the problem is that the trip is not as symmetrical as we stated. So the guy who was on Earth and who left Earth blasted off in his spaceship and went off somewhere, and then had to turn around and come back. He went through a series of accelerations and decelerations. And remember, we said that these laws of special relativity apply for uniformly moving frames of reference. Because he was accelerating, the laws of special relativity don't apply to him anymore. They still apply to the twin who was on Earth. So when our traveling twin gets back to Earth, his brother has aged significantly more than he has. So one other significant element of this is that you might consider certain distances to be untravelable in a single human lifetime. The center of the galaxy is roughly 30,000 light years away. You would probably assume that no human could get there in a single lifetime. Well, if you actually do these calculations, it's 30,000 light years away from our perspective. It's not actually, it wouldn't actually take that long for someone traveling at a significant fraction of the speed of light. So we have an example here. So astronauts traveling at 99% the speed of light travel to Procyon, about 11.4 light years away, and back, which takes around 23. We'll say they stopped there for a little bit. Around 23 years. Now, in their case, 3 years have gone by. But for the space officials who were on Earth the entire time, 23 years have passed. But let's imagine that they didn't come back. What if they just traveled a great distance at a great speed? So if you traveled at 99.99% the speed of light, you could travel for 1 year of your own time, and from the perspective of someone on Earth, you'd go more than 70 light years. 99.999%, you'd go more than 200 light years. So in actuality, if you traveled at a significant enough speed, you could get anywhere within a single human lifetime. If you take this to its logical conclusion, what happens if you actually travel at the speed of light? Well, photons do that. Photons get everywhere instantly. Time does not pass for photons. Photons travel through space, they do not travel through time. And if you could travel at the speed of light, which you can't, spoiler alert, you would get anywhere in the universe instantly. No time would pass for you. Weird, right? So Einstein had to kind of rationalize this. Before Einstein's time, it was generally accepted that the universe is this infinite expanse. Everything exists within it. Einstein decided that maybe the universe actually encompasses space and time. So rather than space and time existing everywhere, they only exist because our universe exists. Moreover, he actually figured out that they're one and the same. Space and time are just different parts of the same thing, which he called space-time. So you've probably heard this expression before. It was Einstein which introduced us to this concept. And in actuality, it makes a lot of things make a lot more sense. So another interesting aspect of high-speed travel is length contraction. And I won't go into this in depth because this is really another side of the same coin. There we go. So sorry about that. Length contraction means that as objects are traveling at high speed, they appear to shrink from your perspective. Now again, if you are one of these, if you're traveling with one of these objects, it'll appear perfectly normal to you. But if you see it go past you at a relativistic speed, it will appear to shrink. And it will only shrink along the direction of motion. So perpendicular, the height of the object stays the same. Now, the reasons for this are pretty much the same, and actually, if you look at the equation, it's going to look very similar. That's pretty much just the opposite of the time dilation equation. Now, the faster you go, the more significant the difference. If you were to travel at the speed of light, the object would shrink to nothing. All right, so some examples which will look very familiar. 87% speed of light, a meter stick would appear to be half a meter long as it went past you. 99.5%, it would appear to be 1/10 of a meter long. And as I said, that's just the length of the stick as it goes past you. The width would not change from your perspective. So time dilation, length contraction, good stuff, real easy, right? Now, let's break down another barrier and talk about simultaneity. So we all know what that means. If two events happen at the same time, we consider them to be simultaneous. But when you start to take relativistic speeds into effect, you realize that things that might appear to be simultaneous maybe aren't quite for all observers. So let's consider an example. So you're watching a train go past you at relativistic speeds, and as the train goes by, you see two lightning strikes at the exact same time. One strikes the back end of the train, one strikes the front end of the train. From your perspective, these lightning strikes were simultaneous. But now, imagine that you're on the train, traveling forward at a high speed. The light from each event takes time to get to you, the observer. And you are traveling towards the event at the front of the train. This means that you'll see the light from the front lightning strike before you see the light from the back lightning strike. From your frame of reference, the two events were not simultaneous. Now, we probably figured this out by now. Who's right? You both are. Everyone's frame of reference is equally valid. We're very inclusive here. So let's consider an example. So this graph represents, in a probably more confusing than it needs to be way, the idea of event A and its area of influence. So event A happens, and then events that can be considered after event A have to fall into this light cone as it expands out throughout the universe. So let's consider a little example. Oh God, falling. We'll be okay.
We want to see it falling for a few seconds.
All right, so imagine that I'm on Earth and I've got a friend on Mars. And at this particular time, Earth is 12 light minutes away from Mars. And I decide to send an email to my friend. So in scenario 1, I send an email to him, and I get an email from him 8 minutes later. Scenario 2, I send my email to him. I get the email from him 16 minutes later. Scenario 3, I send my email. I get one back 30 minutes later. All right, so scenario 1, I send an email. I get an email 8 minutes later. We're separated by 12 light minutes. Who sent the email first?
Mars. Yeah.
Does everyone agree?
Yeah.
Scenario 2, 16 minutes later. Who sent the email first?
Probably a trick question, but I'm going to say Earth guy still.
Scenario 3, who sent the email first?
Earth guy.
Should we assume that these 12 minutes mean that you're sort of are you guys moving towards or away from each other?
Irrelevant.
Okay.
Irrelevant for this example, I should say. That is an important distinction. But so the answer in scenario 1 and scenario 2 is that there is no answer. Depends on where you measure it from. Light from event A did not get to location B before event B happened. In neither of these scenarios, 1 or 2. Now in scenario 3, I sent an email to my friend on Mars, and time passed, and then he sent one to me. Scenario 3, you can definitively say, I sent the email from Earth first. But in these first 2 scenarios, the 2 events were not connected by light. Does that make sense? So the area of influence of my email did not include Mars until 12 minutes had passed. So in scenario 1, Mars is out here. In scenario 2, it's here. In scenario 3, it's finally in my area of influence. Yes?
Is the second one supposed to be a reply to the first email, or just some email?
It's just an email.
Okay, so it's not.
It would be really impressive if you were replying to emails that he hadn't gotten yet.
Okay.
But, I mean, that's more or less the point. The point is that event B was not triggered, could not have been caused by event A. So the concept of before and after are meaningless. Which event happened first depends on where you are when you observe it and how you're moving. So the motion, the relative motion, is important in determining from your frame of reference which event happened first. But to say absolutely which happened first, there is no answer.
The first example, from Earth's perspective, that he sent the email first. From Mars' perspective, he sent the
Yeah, exactly. And that would be the case in scenario 2 as well, because in both cases we sent an email without knowing of the event, of the other event.
Well, isn't in the second scenario then it's possible that Mars guy got the email before he sent it?
Well, no, because it would take 12 minutes for his email to get back to me, right?
Okay, I got it.
There's no way he could have received it and then replied.
Right.
Yeah, because the Mars guy sent it 8 minutes into Earth guy sent it. Okay.
All right, so does that make some degree of sense?
Well, okay, so wait, well, what if I were on, like, somewhere between Earth and Mars? I were just on a spaceship between Earth and Mars. Wouldn't I have, like, a perspective of which one sent it first that would be different from they're both right? Wouldn't
Well, the point is that if you measure it, you are correct. You're right too.
Okay.
So
No right, wrong answer.
the only thing that matters here is that the 2 events are not causally connected.
Right.
Light from event A did not reach event B. Therefore, which one happened first completely depends on where you measure it from.
Okay. Where does you
That doesn't make sense.
But it's not a read, it's not a regarding email. It's just
No.
It's a really important point. The 2 emails may or may not be related. It doesn't matter. All right. So moving on to Einstein's 4th paper from 1905. Well, Einstein took this whole thing, relativity, special relativity, a step further, and noted, and we won't go into the math here, but he noted that as an object travels at relativistic speeds, its mass increases. Now, if I were to throw a baseball to the other side of the room, from our perspective, since it's moving and we're not, its mass actually would increase, but by an amount that you would never be able to measure. But if you're traveling at a significant speed, the mass increase becomes noticeable, and the equation should look very similar. It's actually the same as the equation for time dilation. So the faster the object is going, the more massive it becomes. But remember, that's only from our perspective as we watch the object move. If you are moving, you don't become more massive in your own frame of reference. Now, anyone who took high school physics might remember the Newtonian equation for kinetic energy, E equals 1/2 mv squared. But now we know that mass actually depends on your speed and the speed of light. So the equation actually becomes significantly more complicated. And again, we won't go into the math because it's actually a lot harder than it looks. If you calculate the kinetic energy of an object, you actually get this equation, which again looks similar to our time dilation equation. But you'll notice if you take V and set it to 0, so your object is at rest, this bottom factor goes away. 1 minus 0, square root of 1. So you get, ta-da, E equals mc squared. And Einstein proved mathematically that mass and energy are equivalent. This is the source of energy for nuclear reactors, nuclear bombs. It's how the sun produces energy. And actually, this was a very significant thing to determine because at the time, no one understood how the sun could possibly have burned for as long as it had for Earth to exist. The actual age of the Earth wasn't known correctly at this time, but it was pretty well accepted that it was older than it could possibly be given any sort of method for the sun producing energy. This explained how the sun can produce energy for so long. It's converting matter to energy at an extremely efficient rate. But Einstein still wasn't done. He had to incorporate pesky gravity. This took him over a decade. So he published his theory of general relativity in 1916, and he worked doggedly on it for pretty much that entire time. One of the most impressive things about Einstein, other than the fact that he was possibly the smartest person ever to live, is that he was tenacious. He would not give up when he needed to figure something out. And so the only reason that we got general relativity when we did was his dogged determination to figure out how gravity worked into this mold. Now, special relativity we call special relativity because it's a special case of general relativity, the case where you are not accelerating. It's also important to note that challenging Newtonian gravity at this time was a significant move because Newtonian gravity was gospel for physicists. So to suggest that it might be incorrect under certain circumstances was a big deal. So Einstein thought about it and realized that you could consider a couple different scenarios similar to before where you know, we have our frame of reference and we can't perform any tests to figure out that our frame of reference looks invalid to you. Well, Einstein said, we're standing on Earth, we're accelerating downwards at 9.8 meters per second squared. What if you took a physicist, put him in a box, and shot it upwards at the same rate? So he's accelerating towards the bottom of his box. He or she is accelerating towards the bottom of the box at 9.8 meters per second squared. It turns out that this physicist could not do any experiment to determine whether they're in the flying box or the box sitting on the Earth. There's absolutely no way to tell which scenario you're in. So the conclusion is that both scenarios, again, are equally valid. Einstein, and we won't go into any of the examples here because we don't really have time to get into detail, but Einstein found some really interesting things when he then incorporated our rules about the speed of light. So considering this for different observers, he found a startling conclusion. General relativity states that space-time itself is curved by massive objects. I know that's kind of a big leap, but when you see the equations, you'll know why we didn't go into them. So massive objects actually cause curvature in space-time, and this is what causes gravity. Now, even though photons are massless, they're affected by this curvature in space. And we'll talk about why that's significant in a minute. But to get a better sense of this, consider you've got a flat sheet of graph paper, or another example that's commonly used is consider a mattress. You've got a flat mattress, and you roll a ball across it. The ball's going to move in a straight line. But imagine you put a heavy object in the middle of your graph paper or your mattress. You've created a depression in the object. And now, as you roll the ball, it gets attracted towards the object. The motion is curved in the direction of the object that you put on your mattress. This is how gravity works. The larger the mass, the greater the distortion, the more intense the gravitational field. The force of gravity is a function of the bending of space-time. Now, if I throw an object up in the air and it comes down, we see it take a parabolic trajectory. But it's not actually the object whose motion is curved. It's space-time. The object is moving in a straight line in curved space-time. Weird, right? All right, so yeah, I thought about it, but we're not going to work out his equations for general relativity. The important thing to note here is that these describe how the fabric of space-time works. They describe how our universe works and how things interact gravitationally. That means that if you can come up with a solution to these equations that fits and doesn't violate any rules, it can exist in our universe. So you probably heard a lot of, if you've ever read any of the really out there scientific literature, people predict that we can have negative energy, that we can have wormholes, that we can have, et cetera, et cetera. That's because there are solutions to Einstein's field equations that show that these things are possible. So the first person to find an exact solution to Einstein's equations, and actually remarkably quickly, was German physicist Karl Schwarzschild. And by the way, Schwarzschild or Schwarzschild, I don't know. I've heard it like exactly the same number of people say it the different ways. So first time I heard it was Schwarzschild, that's what I'm going with. So he described the gravitational field around a spherical mass and determined that there was an exact distance, which we call the Schwarzschild radius, at which the escape velocity is so strong it's actually greater than the speed of light. Now, for anybody who doesn't know, escape velocity is simply the velocity you need to achieve to escape an object's gravitational field. So what this means is that if you get a mass condensed into a small enough area, you can have a case where the escape velocity is so high, light can't even get out. The Schwarzschild radius of the Earth, 8.87 times 10 to the negative third meters. Not really significant. The sun's a little bigger, 2.95 times 10 to the third. So those numbers are meaningless because the Earth and the sun are a lot bigger than that. But if you actually get all of the object's mass condensed within the Schwarzschild radius, then you have a black hole. Interesting fact, Einstein really didn't like this, did not like black holes, and didn't actually believe they existed. But we now know that they are a real thing. And there's a couple different kinds of black holes. So there's stellar black holes, which are formed by the death of very massive stars in supernova events, which are super cool. And then there are supermassive black holes, which are formed by... Jury's still out on that one. This is a topic of great interest to astrophysicists currently. A lot of studies have been going on regarding different black holes of different sizes and the formation of black holes. So maybe we'll have an answer soon. That would be nice. But right now, there's no agreed upon theory. Black holes can't be seen because they absorb all radiation. They don't let anything escape. But as matter falls into a black hole, it starts orbiting it. And what happens is the matter collects and forms what's known as an accretion disk. So basically, you've got a large quantity of matter spinning around a black hole, just slowly waiting to be eaten, more or less. And this matter interacts frictionally with itself and through tidal forces with the black hole, and it heats up. And it releases tremendous amounts of energy. So black holes can actually be detected by their accretion disks. Because of this, we know that there is a supermassive black hole at the center of the Milky Way galaxy. It's around 4 million times the mass of the sun. Our nearest galactic neighbor, Andromeda, the supermassive black hole is actually significantly more than 10 million solar masses. Sorry, 100 million. It's like 110. Well, there's a giant range because, of course, nobody knows exactly what it is, but it's at least 110 million solar masses. I don't know why that's funny. But the physics of galaxy formation is still something that we really don't know very well. There is a lot of disagreement in terms of that. And so determining how these supermassive black holes actually form would go a really long way towards answering a lot of questions about the formation of our universe. Now, remember before I mentioned how photons are affected by the gravitational field even though they're massless. This was a really significant point because per Newtonian gravity, if you remember, anyone who took physics in high school, the gravitational force depended on the mass of the two objects involved. If one of those objects is massless, the gravitational force should be 0. So per Newtonian gravity, light should not be affected by a gravitational field. Einstein said this isn't correct. And Einstein has been proven correct. So in the case of a very massive object that produces a black hole, as light travels near the Schwarzschild radius, or the event horizon, its trajectory is bent by the gravitational field. And we call this gravitational lensing, and it's actually even visible around the sun. So it's been observed and it's measurable. It's been observed during solar eclipses that the sun can gravitationally lens light from behind it. This was one of the big proofs that showed that Einstein's theory of general relativity was correct. Now, as light travels away from the black hole, as it's fighting the gravitational field, it loses energy. Now, normally when an object loses energy, it's going to slow down, but we know that light can't do that. So the energy of a light wave is proportional to its frequency. And it's inversely proportional to its wavelength. So a longer wavelength means the lower frequency is lower energy. Higher wavelength, so shorter wavelength, high frequency, high energy. As light travels away and loses energy, the wavelength increases, the frequency decreases. This moves it towards the red end of the spectrum, so we call it gravitational redshift. Now, remember our light clock from before. We're going to use light to keep time again, but we're going to do it differently this time. We're going to measure the oscillations of the wave and use that to be our absolute clock. As light escapes from a black hole or significant gravitational field, the oscillations slow down. Which means if I'm observing light that has been gravitationally affected, I am going to observe time slowing down. So Einstein calculated gravitational time dilation, which you can see incorporates the Schwarzschild radius the metric in there, and effectively, what's that?
I didn't believe in the Schwarzschild radius.
Well, it doesn't prevent him from doing math. I think Einstein's issue with it was that he didn't believe that you could have so the Schwarzschild radius is a thing, and it fit his math, and it made sense. But I think Einstein seriously questioned whether you could get the entire mass of an object within its Schwarzschild radius. So this is a real life phenomenon. This is a thing that actually matters to us. Gravitational time dilation affects right here on Earth. Satellites have to take general relativity into effect. Satellites are further away from the planet, which means they're in a weaker gravitational field. That means their clocks move faster. So if satellites don't take general relativity into effect, their clocks get out of sync with clocks on the ground. This obviously is a huge problem for telecommunications, GPS, everything. Satellites need to be in sync with what's on Earth. So satellites actually correct for general relativity. Now, in the case of a black hole, let's imagine we're watching some poor sucker go through the event horizon of a black hole, and we're watching from a distance. because as they get closer and closer to the event horizon, the time dilation effect is more significant. We would never actually see them pass through the event horizon. Ultimately, the time dilation would be so significant as to be infinite the closer they get to the event horizon. So from our perspective, they would slow down and they would stop before they ever actually made it through. Now, the person going through the event horizon doesn't notice any of this. They just go straight through. Nothing slows down for them. Again, their frame of reference is equally valid and equally dead. As they approach the singularity in the gravitational, inside the black hole, what happens is that the force of gravity on their feet, assuming they're going down feet first, would be so much more significant than the force on their head. They would stretch out and be spaghettified. This is what's known as tidal forces. This is actually the source of the tides on Earth. The fact that on the far side of the Earth from the moon, the gravitational field is less than it is on the near side. That's why we have tides on both sides of the planet at the same time. So on that pleasant note, that concludes my presentation.
Oh, great, perfect. I have a question. Spaghettified is that like, you know, a term they use in the field, or is that?
That's a real term.
Really? I've never heard that.
You've never heard spaghettified before?
I mean, you
I'm
know,
glad I could teach you something today.
only in terms of actually making spaghetti.
Do you actually spaghettify something when you make spaghetti? I'm not even sure.
Yeah, zucchini for sure.
Oh, okay, that's good.
So like, you were talking about how the light frequency decreases as they go away from the black hole.
Yes.
So like, isn't there like what happens when they? What is it like? Is there a limit to that or something? You know what I mean? Like, won't light eventually like have no frequency at all?
Like exiting the area of effect, is that what you're talking about?
Huh?
What exits the area of effect? Is that what you're asking about? Oh, is it only when it's in within wait?
As it's struggling with the gravitational field, as it's exiting, it loses its energy. It loses energy. Now, eventually, when it's no longer, if it gets a distance away and it's no longer affected by the gravitational field, it would, it wouldn't be losing energy anymore.
Oh, but it wouldn't revert. It would just stay with the same wavelength of
Right.
energy it took to get through the.
Right. Exactly.
So the reason you were saying the clock thing is, at a lesser degree, the same thing happens with any massive thing on our planet.
Yeah. Any gravitational field causes gravitational time dilation.
So that the satellite thing has nothing to do with a black hole. It has to do with our Earth.
But it has to do with gravitational time dilation. So it doesn't necessarily have to do with a black hole, but it's,
Okay. But
Yeah.
It's not just black holes.
right. It's not just black holes.
Okay.
Yes. Yeah. Any mass it causes gravitational time dilation as light fights the gravitational field.
Black holes are just like an extreme example.
Yes.
You said that a human traveling at the speed of light could get basically anywhere in a human lifetime.
They could get basically anywhere instantly if they were traveling at the speed of light.
Okay. So I'm looking at the night sky and I see starlight that's 4 million years old, right? It doesn't hit Earth.
Right.
It was created 4 million years ago. You see it, your eye sees it 4 million years later.
Right.
But that took 4 million years to travel at the speed of light to my eyeball.
Yeah.
If I was traveling at the speed of light, but you're saying I could get there within a lifetime. That's
Yes. From your perspective, it took 4 million years to get to you from that star. But if you were traveling at the speed, or say from the perspective of the photon got to you instantly. You could ask the photon how long the trip was. It would tell you, I just left.
It would tell you, I have no idea what time it is.
I don't speak English.
I'm not. Yeah.
What is how long? What is that?
Aaron?
What do you mean, Seth?
Yeah, because I have two questions.
Oh,
Okay,
God.
so you mentioned earlier, as things travel faster, their mass increases.
Yes.
But from its own perspective, it's the same mass. How do we know, and how does that even like matter?
Those are your two questions?
No.
Or do you have another question after that?
That's question one.
Um,
I will hit you with another one immediately after.
So how we know, again, so I didn't go into the math of it, but the same way you could mathematically prove the time dilation, through more significant and more difficult math, you can mathematically prove the, yeah, that's the one. You can mathematically prove the mass increase effect. In terms of why it matters, well, I mean, in the same as any of these other cases, it matters because if you were traveling at high speeds, it would be really significant that that object had a bunch more mass from your perspective as it hits something else, or, but
it directly led to basically nuclear energy.
yeah, I mean, from the,
I mean, maybe the power plants are wrong, I don't know. Well, if you're traveling at super high speed and you have super high mass, would you see time dilation start to happen around? Or?
if you're traveling at high speed, you would see, so time dilation would affect anything that was not moving with respect to you, or sorry, that was moving with respect to you. So if you're traveling at a high speed, you see everything go past you at a high speed. Time dilation affects everything else, if that makes sense. So if you measured the time of something you went past, you would get a greater result than that stationary observer would. Stationary. Again, it's all relative.
So for the mass thing, you were saying, when you were saying it earlier, you were saying like, if you throw a ball and you're going at a relative speed, then from somebody who's standing still, the ball is heavier, right?
Yes.
So
more massive.
So does that, what I don't understand that, does that mean that they would, like, if you take into account gravity then, does that mean that they would see it hit the ground before you?
So they see it what?
Hit the ground before you because the mass is stronger, therefore.
Well, so the mass of an object doesn't affect the rate at which it falls. Did you have another question?
Yeah,
Oh, yeah.
So there's a black hole in the middle of our galaxy that's sucking stuff in. And when it sucks stuff in, its mass grows.
Mm-hmm.
And if its mass grows, then its gravitational force grows.
That is true.
So is it inevitable that eventually it will suck us all in?
No, actually. So the thing is, it's increasing in mass at a slow rate, but there's also, black holes also actually lose mass. And that actually was just proved pretty recently by Stephen Hawking, what's known as Hawking radiation. And it involves quantum effects that we won't go into because, I mean, if you think this is weird, like quantum, it's really weird. But so it actually, it's also continually losing mass as it's sucking stuff in. But the rate of increase is not significant enough that it's going to gobble us up. Ultimately, where some models suggest that we'll collide with the Andromeda galaxy in 4 billion years or something like that. And that'll probably be the next really significant event for our galaxy.
I have one comment. So if you like this stuff, you're assuming we'll be interstellar.
Well, a few weeks ago,
Well, they introduced love.
That's what Einstein was missing the entire time. Love.
But it's good.
I like that movie. I saw that a while ago. Yeah. Does anybody have any questions about other random things either?
So gravity, if I'm in a big spaceship, right, long, I don't know how long, really long, and the back end of my spaceship is facing a black hole, and it's trying to get away from it, so then I've got enough force to move very slowly away from it. Time will slow down on the back of the ship more than it will on the front of the ship, right, because of gravity.
That's true. You'll also get stretched out. Your ship might become spaghettified. You'd notice getting spaghettified. That's not a relativity thing.
Wait, you said that they wouldn't notice.
They wouldn't notice passing through the event horizon. Like, they wouldn't notice time slowing down.
Oh.
They'll notice they're getting spaghettified, probably. I'd imagine.
But it takes an instantly long time to pass through the event horizon.
From the perspective of a distant observer.
So the twin paradox thing earlier, I totally didn't get it. Because like you were saying the reason the Earth person aged longer is because the person in the spaceship is accelerating. But from the person's spaceship person in the spaceship, then the Earth is accelerating, isn't it? From their perspective.
So,
I don't know how that applies.
so from their perspective, let's see. So in order to accelerate, a force has to be acting on you, right? So the acceleration is not actually relative. Acceleration requires that you are experiencing a force of some sort.
Okay.
I don't know if that makes it any clearer.
In the case of the ball off the train, which I can understand better, when you were saying how like they're going at different speeds, that's after the ball is going at a constant speed. But while it's accelerating, both observers would agree on the acceleration.
So,
like, you know what I mean? Like, if you threw the ball 10 meters per second on a train.
For these examples, we're generally considering like the ball is shot out at a constant velocity. So these are simplified examples that don't take acceleration into effect. So when I say I throw a ball forward, it's, you know, my vehicle had to accelerate, the ball has to accelerate to whatever speed I throw it at. That's definitely true. But it's sort of like you know, whenever you do a problem in high school physics, it's always, everything's perfectly spherical and it's a frictionless scenario and et cetera, et cetera. So we're not taking into account the effects of acceleration. Acceleration would muddy the waters. And as far as the mathematics of that, that's not something I've worked on. But it would be, in terms of whether you would agree on the acceleration, well, I guess it really actually doesn't, because you'd agree, I would agree with your frame of references measurements. Yeah, you'd see the same acceleration rate.
Yeah, that's what I meant.
Yeah. I believe. Hopefully I'm not saying something incorrect.
But with the spaceship example, so does it matter, like, if they never go at a constant rate, if they go out and accelerate the entire time and then turn back around and then decelerate and then go in reverse, if they're accelerating or decelerating the entire time, there's no time then that effect won't happen?
No, so you could measure their speed at any point in time and calculate the difference in your time for their time. They're accelerating. You're sitting here on Earth watching them speed up and slow down, but you're still watching them move quickly. Right? So even if they're speeding up and slowing down, you can calculate the time dilation. It just would be way more complicated because you basically just have to calculate it at every instant to figure it out, like the exact amount that it is. Yeah. But you would still observe them moving at high speed, so you would still experience time dilation. It's just that these exact rules wouldn't apply for them because they're the ones experiencing the force.
Well, I mean, you're both experiencing the same force, but the actual resultant acceleration is less for the guy in the spaceship, or is more for the guy in the spaceship because it's less massive.
We're not experiencing the same force. We shot this guy off in a spaceship while somebody stood there on Earth.
Right, but what I'm saying is, yeah, there's a force downward on Earth that creates negligible acceleration for everybody else, and then a lot of acceleration for that guy. So you are experiencing acceleration, but not enough to like through it.
So you're kind of, I think you're confusing a couple of concepts here. So he was accelerated upwards. So if you're standing on Earth, the normal force counteracts the downward acceleration due to gravity. So the normal force keeping me from falling through the ground, I'm not actually experiencing acceleration because the net force is zero. So if we shoot this guy upwards, he is experiencing acceleration as he's shot off into the sky.
But if you jump or something, you're pushing down on the Earth. So the Earth is experiencing that force.
Right.
Yeah.
It's just that it's so massive that it doesn't really matter. That's what she's saying.
Yeah.
Right? Isn't that right?
I'm sorry, I'm not getting how this relates to the.
Well, so Luis was saying, like, why is it that the acceleration is affecting that one guy's age and speed so much more than ours? And I'm saying we're both experiencing the acceleration that kind of messes with relativity and affects our experience of time, but it's a much greater distortion for the individual guy in the the rocket ship because that same force is accelerating him so much more.
So I think you're putting overdue emphasis on acceleration. So the laws of special relativity assume that we're dealing with a uniformly moving frame of reference. So the acceleration is not taken into account. It is a special case of relativity. General relativity describes how space-time is affected by massive objects, and ultimately you can derive special relativity from general relativity. General relativity will take into account acceleration, but everything is way more complicated. So our case, our special relativity example is assuming we're not accelerating. So, I mean, if your guy is jumping up and down for some reason on Earth and constantly experiencing acceleration because of that, that affects things. But eventually you have to get into the really heavy math to figure out exactly what the effect is. But in terms of speeds, what the time dilation effect is dependent only on the speed that you're traveling. Does that make sense? Well, that's exactly. Any questions?
What's your background?
I got a question.
You just watch a lot of Star
He's an astrologist.
Stop it. So I double majored in computer science and astrophysics at Pitt. I think there was a question on the phone. Did I get that right?
Seems. Yes. Can you hear me?
Yes.
Okay. It seems like everything is kind of boiled down to time and speed, and it seems like that acceleration's the only thing that changes reference frames. Is that an oversimplification because we're looking at simplified math things, or is that really all that ends up mattering is kind of time and speed?
In terms of special relativity, that's pretty much it. Like, I mean, length is affected just as much as time is, but speed is the only thing that affects or that determines the degree to which something is affected. And for special relativity, we're simply just taking acceleration out of the equation completely.
Okay. And for the weird conclusion that is the twin paradox, that's not really a paradox. If you could somehow go from 0 to speed of light, that would completely change this then, right?
Well, so I mean, with light is never accelerating or decelerating, right? Photons are always traveling at the speed of light. So, I mean, photons have their own rules. And again, they get everywhere instantly. I don't know if this answers your question or not, but I mean, that's the way light works, right? So light is instantly going when an electron emits a photon, for example,
right.
It's instantly traveling at the speed of light.
Right, and so if instead of the twins being two people, they were two electrons, because the electron didn't accelerate, there wouldn't be this age gap. Am I understanding your explanation of that twin paradox correctly?
Well, there's still so we would still have to turn around and come back.
Okay.
So there's still a directional acceleration.
All right, I get
it. So it's still, it doesn't, or special relativity doesn't apply in that circumstance.
If the universe is donut shaped and he went around the entire universe, would that change it? Because it wouldn't have a directional acceleration?
I don't know. You got me there. I have asked that question myself, to myself.
Okay.
I don't know the answer.
Okay.
Yeah, for some reason I didn't answer myself.
Thank you.
All right. Thank you.